This is Math 251, and we're in section 12.8, talking about maximums and minimums, or optimization, for functions of two variables. I'd like to start just by a comparison with what you already know about optimization in Calc 1 for just a function of one variable. If, for example, you graph a curve, it's fairly easy visually to identify local maximum and local minimum points. The way that we usually identified those was by taking a look at places where the first derivative was 0. Right? Here the slope of the tangent line is 0. Or it actually might have been undefined, although I don't happen to have any illustrated in this particular picture. So our test to identify possible locations of maximum and minimum points was where is that first derivative equal to 0 or undefined. We have something similar happening for a function of two variables. Let's imagine that this surface is a function z is equal to f of x and y. You can locate maximum points, like there's the top of a hill, it looks like right about here. That would be a local maximum. Excuse me. Or local minimum points. Looks like there might be one down in here somewhere. And in order to actually find those points, we also use something to do with the first derivative, similar to the first derivative test for the single variable functions. Of course, in the case of a multivariable function, there are actually two first derivatives. There's an f sub x and an f sub y. And our test is going to say that they both have to equal 0 or be undefined in order for our point xy to potentially give us a max or a min. Now, once we have these potential maxes or mins, which we usually call critical values, the next thing we do, we have to test them, right? In Calc 1, you learned that one of the ways to test them was using the second derivative. A positive second derivative meant a minimum, a negative second derivative meant a maximum, and a second derivative of 0 or undefined was actually an inconclusive test. Again, with our multivariable functions, we will use the second derivative to determine whether our critical values are maximums, minimums, or maybe something else. But instead of a single second derivative, we actually have several second derivatives, right? We have f sub xx, f sub yy, and the mixed partial f sub xy. In order to use the second derivative test, we have to define this value capital D, and notice that it's just an expression that involves all of the second derivatives. The product of f sub xx and f sub xy, subtract the square of x sub xy. We go ahead and plug our critical value into there, and then we have these descriptions, I guess I'm going to call them, of what's going on. A positive D and a positive f sub xx gives us a minimum. Positive D with a negative f sub xx gives us a maximum. A negative D value is what we're going to call a saddle point. We'll talk a little bit more about that later on. And then if D is 0 or undefined, our test is inconclusive. We're going to go ahead and organize that information in a little bit of a chart. So let's organize again our information for quick reference. If we have a critical point where f sub x and f sub y are both 0, then D again is defined as the product f sub xx times f sub yy minus f sub xy squared. And we said that if D is negative and f sub xx is positive, then we have a minimum. We said that if D is negative and f sub xx is also negative, I'm sorry guys, let me go back. If D is positive and f sub xx is positive, we have the minimum. If D is positive and f sub xx is negative, we then have a maximum. If D is negative, here we go, then it doesn't matter what f sub xx is. We have what's called a saddle point. And a saddle point is one of those places where from one direction it looks like a minimum, and another direction it looks like a maximum, just like a saddle. The hyperbolic paraboloid is the easiest illustration of that. Right here is what you would call a saddle point. It looks like a minimum from this direction, but if you looked in from the end of the saddle, it would look like a maximum of the cross section. So a saddle point looks like a minimum from one perspective, but a maximum from another. And then finally, if D is 0 or undefined, then our test is inconclusive. All right, so we'll use this little chart as we evaluate our critical points to determine what's going on at each critical point. In our first example, we'd like to find and classify the critical points for this function. And I need to start by, again, locating critical points. This is the first derivative test. So f sub x would be 4x cubed minus 4. That has to equal 0. And f sub y, which is 4x cubed minus 32, also has to equal 0. This was a particularly nice situation because this equation only involves x, and that one only involves y, which is the simplest situation. Good grief. 4y cubed. Gotta watch my variables here. All right, that was 4y cubed from there, right? All right, so simple to solve because they're both just one variable equations. Basically, this one would say x cubed equals 1. So x would be 1. And this one would be y cubed equals 32 over 4 would be 8. So y would be 2. So the only critical point we get in this case is the point 1, 2. We're now going to test this critical point to decide whether it's a maximum, a minimum, or a saddle point. And in order to do that, I am going to need all of the second derivatives. So let's see, f sub x would be 12x squared. F sub y would be 12y squared. And then the mixed partial, f sub xy, in this case it would be 0, right? There are no y's here, so when I differentiate with respect to y, treat it as a constant, and I just get 0. So D is the product of these two. Minus the square of the mixed partial, so in this case 0 squared, which is going to give me a D of 144 x squared y squared. Now typically we'll have more than one critical point, so I'm just going to sort of show you how I usually organize this information, even though in this case with just one critical point it might be overkill. But usually what I do is make myself a little chart, and for each critical point I evaluate D and f sub xx, and then I draw my conclusion. So in this case, our only critical point was 1, 2. Notice that if you plug that into D, certainly with the squares there, you're going to get a positive value. We don't really care that much what that value is, just if it's positive or negative. And f sub xx, again, if you plugged in x equals 1, you'd obviously get 12, which is positive. So a positive D and a positive f sub xx, if you just glance at the chart at the top of our page, our conclusion should be that this is a minimum. Now, I want to make one more point here, and I'm going to do this for this particular one, but I will tell you that in general, I'll probably skip this last step most of the time. I'm perfectly fine you getting to here. We have a minimum that occurs at this point, but we have not yet found the actual z value. So the minimum value of something that I don't know yet occurs at the point 1, 2. And to actually find out that minimum, I could plug my point 1, 2 back into the original function. Which would give me 1 to the 4th plus 2 to the 4th, mine's covered up here, minus 4 times 1, minus 32 times 2, plus 10. Sorry, my document camera was sitting right on top of my function. I couldn't see it. So we'll just plug that into the calculator. And I'm getting negative 41. So negative 41 is the actual minimum value, and it occurs at the point 1, 2. Of course, on the graph, that's just going to look like a min at 1 to negative 41. All right, I've actually got this one graphed for us on Maple, so let's go ahead and click over there so we can take a look. Let's see, back to the top of the document. Here it is. So let's see, you can see that I've got, let's see if I can move this over just a little. There we go, it's a little bit better. So you can see I did my with plots, and then I did the implicit plot 3D, and here's our function. And here's the graph. And you can see down here, it does just have the one minimum. If I were to rotate this a little bit, you can see that it doesn't appear to have any other minimums or any other suggestions that there's going to be a max or a min. It's a little harder to locate the exact point, but if I kind of look in from the top, you can kind of see down here where the minimum is. There's the y equals 2 right here. And there's the x equals 1. It certainly seems like a reasonable location for the minimum. And as far as the z value of negative 41, again, if I kind of put this horizontal, that also seems like a pretty reasonable z value down there. So you can see with Maple that we have indeed found the correct minimum. All right, let's try another one. I would like to find and classify, again, critical points for this function. And so we'll begin, again, just by finding the critical points. That's our first derivative test. So I take my first derivatives, which would be 2x plus y squared minus 2. That needs to be equal to 0. And then also f sub y, which would be 2xy, and that's it, also needs to equal 0. Okay. Now this one's not quite as simple to deal with, simply because we've got both x's and y's in both equations. But this is clearly the simpler equation, so I'm going to work with this one. This actually says that either x equals 0 or y equals 0. So what I'm going to do is just plug each of these values back into the other equation one at a time and see what the opposite variable turns out to be for each one. So if x equals 0, this equation would become 0 plus y squared minus 2 equals 0. So y turns out to be plus or minus 2. And if y equals 0, then this equation becomes 2x plus 0 squared minus 2 equals 0, so x equals 1. So I actually ended up getting 3 critical values this time. I have 0, whoops, I'm being careless today, 0 and positive the square root of 2, 0 and a negative square root of 2, and then 1, 0 for this one. All right, let's test our critical values using our second derivative test. I will need, first of all of those second derivatives. So f sub xx looks like it's just going to be 2. F sub yy will be 2x. And then my mixed partial, f sub xy, with respect to y here is going to give me a 2y. So D is the product of these two minus the square of that one, which is 4x minus 4y squared. All right, so we've got everything we need. It's just a matter of putting the pieces together now. So for each critical point, I need to know what's going on with D, with f sub xx, and then I need to draw my conclusion. And I'm going to start with 0 square root 2. If I look at D, if x is 0, and I'm subtracting 4y squared, that's got to be negative. And once D is negative, it really doesn't matter. It's a saddle point no matter what. Let's go with 0 square root negative square root 2. And I don't think that's really going to change anything. My first term's still going to be 0, and I'm subtracting something positive because of the square, so it's going to be negative again. And this is another saddle point. Last, I had the point 1, 0. Plugging that into D would give me positive 4 minus 0. That will be positive. And my f sub xx is 2, so that's always positive. So positive, positive, that gives me a minimum. So I'm actually not going to go ahead and get the z values. You certainly can. It's just a matter of plugging them back into the original function, of course. But I'm just going to say there's a saddle point at 0 square root 2, another saddle point at 0 negative square root 2, and a minimum at 1, 0. If you want the actual z values of those, again, all you would have to do is plug back into the original function. All right, so once again, let's take a look at this on Maple, see if we can see these interesting points. All right, so here's the graph, the function that we were working with right here. And we were supposed to have a minimum at 1, 0. There it is, actually right there. There's x equals 1. That's right on the x-axis since y is 0, and you can pretty clearly see that minimum point right there. And then as far as the saddle points, they are at plus and minus the square root of 2 on the x-axis where y is 0, so roughly 1.4 and negative 1.4. Right about here and about here. Notice that from this perspective, they almost look like maximum points, but coming around this way, let's see if I can twist this just right, you can see that they would be minimum points going in that direction. So here versus there, they look like a minimum, but also a maximum. That's like that center point on the saddle where someone would sit. So those two saddle points, one on either side, here and here, and then the one minimum right there on the x-axis. All right, we will pause here and we'll pick up this section in the next video.